SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the Applied Thermodynamics course, Module 5, Refrigeration and Air Conditioning Systems. Till this point of time, we have covered 5 lectures on this module. The first 3 was focused towards refrigeration systems, that is vapor compression systems and vapor absorption refrigeration systems. In addition to that, we have discussed about refrigerants, their applications, their designations and their commercial names. And in last 2 lectures, we dealt with fundamentals of psychromatics and how those concepts are used for air conditioning processes. So, in the air conditioning processes, we discussed about humidification, dehumidifications, evaporative cooling, adiabatic mixing, and side by side we discussed how the properties of moist air is going to change for certain processes. Today, in the same line, we will discuss about cooling towers and air washers. So, this is again a application oriented with respect to air conditioning applications, and to some extent you must have aware of cooling tower applications in the steam power plant. And also in a similar line there is also air washers. So, this air washer is nothing but a conceptual things, that means in a layman sense we say it is a washing of air. Now, while doing the washing processes, there are certain requirements that what are the need for the users, accordingly air can be conditioned to fit into the required applications. So, when I mean conditions, it means the properties of moist air, that is its dry bulb temperature, wet bulb temperatures, humidity ratio, relative humidities, all these needs controlled in some fashion, so that we can achieve a desired air conditioning requirement. So, this is the last segment of this lecture series on this module, that is refrigeration and air conditioning. So, we will be dealing with mainly cooling tower and air washers. So, although we have seen that cooling tower applications is one of the important aspects in a steam power plant, but side by side we are fitting into psychromatics because this cooling tower requires the knowledge of moist air and how the air conditions can be controlled, so that we get the required applications. When you dealt with cooling tower for steam power plant applications, their main focus was to cool the warm water that is left from the condenser of a steam power plant, and then that water needs to be conditioned. That means, we call this as that returned water that goes to the condenser back to the again. So, it is basically circulating water and controlling the environment of water or desired condition of water which needs to be recirculated again to the power plant. So, this is how the philosophy of steam power plant requires the knowledge of cooling tower. But other approach is that if our application is oriented towards the requirement of moist air at the exit. That means, when you dealt with cooling tower for steam power plant applications, we are really do not bother what is the exit condition of air, what is the inlet condition of air. Normally, the inlet condition of air is atmospheric, and we do not really bother about the exit condition of the moist air that comes out. Rather, we are mainly dealt with requirement of water or returned water that needs to be sent back to the power plant. But side by side, other way of looking at is that through this water circulations, it is also possible to control the condition of moist air that comes out from this cooling tower. So, there is two possibilities or two applications that we can use this moist air one way. Other way is that you can use this water which is returned back from the cooling tower. So, this is the two broad sense of requirement or applications for cooling tower. Just to give the brief introduction about the cooling tower, so what I can say is that the power plants invariably discharge considerable amount of energy to the surroundings by heat transfer. So, it is carried away by water or nearby lakes. So, what happens is that normally the release of water from a steam power plant goes directly to the river or pond or lake nearby. Many a times what happens when there is a scarcity of water, then people explore the possibility of a cooling tower. That means, water which is supposed to be exhausted and that needs to be recirculated. So, that is what conditioning of air water is required, because it is a recirculated water. So, when in a closed cycle circuit, when the water needs to be recirculated in a steam power plant, the role of cooling tower is very vital. So, cooling tower provides an alternative in locations where there is a scarcity of water reservoirs and concern towards environmental limitations. Of course, they are also used to employ chilled water for applications in the industrial scale and air conditioning requirements. The cooling tower either operate by natural or forced convection, and they can be counterflow, cross flow, or any combination of both. So, this is how the schematic of cooling tower is represented. So, what we see here is that there is a fan. So, in this case, this is the case where it is a forced convection methods, where the fan, in that fan what happens when sucks the air from the bottom. So, you can see the air enters to the tower at state 3 through these passages, and because the fan rotates, it sucks the air from the bottom, and the air outlet goes in the top. So, when the air goes out, it is now moist air. When the air enters, it is normally atmospheric air at certain conditions. Now, when the air goes out, it has contains some water vapor at state 4, we say omega 4, its humidity ratio, which is higher than omega 3. Now, how this humidity ratio increased? Because the humidity ratio of air is increased because we are spraying water or warm water, typically at condition 1, where that is warm water is inlet and it is sprayed, it is in a spray form. So, by doing this spray, we are essentially breaking this content of water into teeny droplets, so that it can so that heat transfer processes can be enhanced. So, in the sense that it takes the teeny droplets gets absorbed in the air. So, by virtue of it, the humidity ratio of air increases, and side by side the content of water, when it comes back, the water is again collected in at the bottom of the tank, which is in the liquid state. Now, through this process, and again the whatever condition air that comes out and stored in this thing, it is returned back, and typically the mass flow rate of water that comes in and mass flow rate of returned water, that they are normally same. I mean, in a cooling tower they are maintained constant, but what happens by virtue of these things, your temperature drops, because it was initially sent as warm water at T1, and when the returned water has temperature less than T1. That is the main requirement, because the returned water needs to be temperature needs to be less here. And side by side we also have a provision of makeup water. What is the makeup water requirement? Now, obviously, when the air interacts with the stringy droplets, it carries it takes out moist, it gets this humidity ratio is increased. So, because its humidity ratio increase, means that some of the water vapors gets absorbed in the air, and as a result the concentration of water which is supposed to be there, it comes out. So, there is some provision that we need to add the makeup water, and the requirement of makeup water is nothing but the increase in the humidity ratio, that is omega 4 minus omega 3 multiplied by the mass flow rate of air. That much amount of makeup water is required here. So, this is how it operates. So, this already have explained this fact that warm water enters and state 1 and spread from the top of the tower. Falling water passes through the series of baffles, and they are mainly intended in breaking the droplets to promote evaporations. Atmospheric air at state 3 is driven from the bottom by a fan, and it is drawn upward opposite to direction of the falling water droplets. Now, when two streams interact, a fraction of air entering liquid water stream evaporates into moist air and leaves upward at state 4, that is out of the tower. So, by this virtue process, the humidity ratio increases from its entering state, that is 3. Now, liquid water at state 2 leaves the tower from the bottom and at lower temperature than that of state 1. Now, since some of the incoming water is evaporated into moist air stream, so an equivalent amount of makeup water is added at state 5, so that return mass flow rate of cool water equals to the mass flow rate of warm water entering at state 1. So, basically we need to control m dot w. Now, to control m dot w, we need to provide makeup water. This makeup water is required because some of the water droplets or water vapors are carried away by the air. Okay. Now, let us see that how we can do some modeling analysis for a cooling tower. So, one way of looking at this process is that we just simplify in a control volume container, where at state 3 air enters, and it is mainly at atmospheric air, and its conditions are normally defined in terms of its mainly relative humidity is 5, and when it goes out, its condition is T4 and phi 4, or we can some way we can say it is humidity ratio at state 3 on state 4. That liquid water enters at a conditions T1 and m dot 1, liquid water leaves out at m dot 2 condition state 2, and makeup water is added at different, of course, that should be at different temperature T5, and also it is m dot 5. So, to do this analysis, we make the certain assumptions. Those assumptions are: heat transfer with surrounding is neglected, power inputs to the fan of forced convection of the cooling tower is negligible relative to the other energy rates, pressure is maintained constant throughout, that is 1 atmosphere. Moist air streams are regarded as the ideal gas mixture adhering to the Dalton's model. So, you can also apply Dalton's model, that is law of partial pressures. Now, here the main mathematical equations that is used here, and that is mostly mass and energy balance in a steady flow operations. And here the one of the main intention or application for the cooling tower design is that we try to see that what is the amount of air that we are that is going to be reused for this cooling tower. That means, to change the condition of water, and typically these derivations are made with respect to a power plant application, that is steam power plant applications, where liquid water at certain flow rate and temperature is allowed to enter the tower, and we expect that same flow rate of water that has to be released or returned back to the power plant, but at a different temperature or lower temperatures. So, if you say the allow the temperature of water that comes from the power plant, mainly this comes from power plant, and this is at condition T 1 and m dot 1, and when the water goes out, that means returned water again back to power plant, we expect that m 2 dot should be equal to m dot 1, that is same flow rate, and of course, T 2 should be less than T 1. That is the requirement for the power plant, that temperature should be lower than this. And to have this problem, we require some certain quantity of air flow rate that has to be pumped into the tower. So, this is done through a fan, and we are controlling that fan, and so that air can be sucked in to the tower. And to have these conditions, the air exit conditions could be like T 3, phi 3 is the inlet state, and T 4 and phi 4 is the exit state. So, the first equation that we are going to use, that m dot A 3 is equal to m dot A, that is dry air, that is say air flow rate remains same, maybe in 4 and 3 and 4 are equal, and with respect to water vapor we can say m dot 1 which is enters, and this is in the liquid state, m dot 5 which enters, that is also in liquid state, and m dot V 3, that means mass of water vapor which is present actually in the air at state 3. So, that is the mass flow at the inlet, and what goes out is the return water at state 2, that is m dot 2, and m dot V 4, V 4 is the mass of water vapor present in the moist air at state 4. And so, from these equations we can say that we expect m dot 1 to be m dot 2, that means water flow rate should be remain same. We can include that introduce omega 3, so that we can quantify what is m dot V 3, that is m dot omega 3 into m dot A, and m dot V 4 is equal to omega 4 into m dot A. So, from these equations, and when you simplify, we can find out what is the m dot 5. M dot 5 means it is the amount of makeup water required at state 5, m dot 5. So, that is the first thing, that is nothing but m dot A omega 4 minus omega 3. Now, look, similar way we can do the energy balances, energy balance at state 1. So, state 1 is water is in the liquid state. So, m dot 1 HF1, and HF1 is the enthalpy of liquid water at state 1, 1 means at temperature T 1. And what the second part is air, air has two components, it is m dot A HA3 and m dot V3 SG3. So, it is in the vapor state. So, see this is the water vapor. So, m dot V3 into SG3, and state 5 is again in the liquid state. So, it is written in the HF5, and state 2 again liquid state, so it is HF2, and state 4 is air plus water vapor. So, it is m dot A HF4 m dot V4 Hg4. So, this is how the energy balance equation was used. So, and now we have m dot 1 is equal to m dot 2, m dot 5 is equal to m dot A into omega 4 minus omega 3, m dot V3 is equal to omega 3 into m dot A, m dot V4 is equal to omega 4 into m dot A. So, after putting this, these energy balance equations can be solved for m dot A. So, this equation can now be solved for m dot A. Now, if you look at this m dot A is nothing but the mass that enters into the cooling tower, m dot 1 is the mass, that is water that enters the tower. So, you can find a ratio, that is m dot A by m dot 1. So, this is nothing but your the ratios in terms of their enthalpies. So, this is a simple expression we can have mass flow rate of air required for the cooling tower. Another equation that we have to use, that how much mass of makeup water is required for the tower. We also use some terminologies in the cooling tower for the design perspective point of view. One is approach, that this approach is nothing but the temperature difference between inlet temperature of water. Please remember, it is the inlet temperature of water, in this case is nothing but T1, and WBT of inlet air. Inlet air comes at state 3. Now, at state 3, the wet bulb temperature of air at state 3. The other parameter of interest is the range. This range is the temperature difference between the inlet and exit state of water. Range is nothing but the with respect to water, and approach is nothing but the inlet temperature of water and wet bulb temperature of inlet air. So, these two expressions are very vital. So, we should remember what is approach and what is range. Next important aspect, now we are going to deal with the air washers. So, air washer in a layman sense, that means we are washing the air for a conditioning processes. So, to get these conditioning processes, the while washing we can have the state of air at different positions in a psychrometric chart. So, based on that we can say what is the actual air conditioning processes that happens, and in fact this air washer philosophy concept in thermodynamic sense will let you know that this concept can be used throughout the air conditioning applications. So, let us see that what this air washer concepts, although it is just a concept, but we can schematically represent in this fashion. So, what a air washer? It involves the flow of air through water spray. So, during the course of the flow, what may happen, that air may be cooled or heated, humidified or dehumidified, or simply adiabatic saturation depending on the mean surface temperature of the water spray. So, till the in our last lecture we talked so many processes like humidification, dehumidification, heating, cooling, then we have adiabatic saturations, we have evaporative cooling, mixing. So, all these processes are possible. Now, when you say all these processes, we are try to locate these thermodynamic states in a psychrometric chart, and if it is possible to locate, then such a process can exist. Now, if it is exist, practically how you can achieve this? So, that is the concept of air washer. So, if it is a feasible process in a psychrometric chart, I mean how we can achieve this. So, this is how it is represented conceptually by this process. So, what happens? This is of course a similar concept what we have in a cooling tower, but it is presented in a different context. So, what we have is that we have a container and in the bottom of the container we have some water, and this water is pumped and there is a external heater or cooler. That means, this is a arrangement where we can have heating process as well as cooling processes. Water can be pumped, and when it pumped we can on the top we can spray the water. I means we can enter water, we can make a teeny droplets and try to spray, and through this process we have also a passage in which air can come in. That means, air may be at one particular state, that is state 1, it is coming and it goes at a state 2. So, this from 1 to 2 the many thermodynamic processes possible. So, what could be there? Air can be only humidified, that means there is no change in temperature. Air can be dehumidified, that means we can regulate this the spray, that the process we cannot have this so that we can take out the water vapors, or that means exit state of water will have less humidity less than inlet state. The other possibility is air can be heated. So, there is a provision of heating, and there can be cooling, air can be cooled, there is a provision of cooling. So, all these processes are possible, and we have also the provision that water can be cooled or heated externally, and there is a recirculating pump, that means it can be also circulated in the circuit. The eliminators plates are provided to minimize the loss of water droplets. Now, here we are trying to analyze that what are the how you are going to model our conditioning air. So, consider a thermodynamic changes of state of air when it goes from the state 1 to 2. This change is due to mean surface temperature of water droplets, which is equal to temperature of water. So, here you are assuming that surface temperature is equal to water temperatures. That means, surface temperature of water droplets is equal to the water temperatures which exists at that state, and the droplets of water acts as a wetted surface. So, means that they act as a wetted surface through which both sensible and latent heat transfer can take place, and the direction of heat transfer depends on the temperature and their vapor potential. What is the capacity? That means whether they have ability to transmit water vapors, or they have ability to not to transmit the water vapor. So, under those conditions it depends the direction of heat transfer, but there is a limiting processes when and of course, when you talk about this point, that ability of transferring these things, then in such cases those processes can be designated in a psychrometric chart. So, we have shown so many processes, I will come back later. So, they can be designated in a psychrometric chart, but the limiting situation would be such that limiting process is that along the condition line tangent to the saturation line drawn from this initial state. So, if you draw a line tangent to the saturation line and from its initial state, that is the limiting processes we can. That means, we cannot go beyond this saturation line. Whatever things we have to do, we have to be within the saturation line, because that is the limiting case for a psychrometric chart drawn at the atmospheric conditions. Now, let us analyze that how you are going to designate these things. And now, let us say that we are at state 1, which is denoted in this psychrometric chart, and this state 1 is nothing but state here, and state 2 can be any locations, any other location on the psychrometric chart, and that is designated as 2. Now, here I have noted at A, B, C, D, that means state 2 are different locations in the psychrometric chart, and that is represented here. So, if I say a process 1 to 2A, that means if I am going in these directions from 1 to 2A and I reach another locations 2A, then such a through this process we can see its humidity increases, and you also see the temperature also increases. So, it is a process is called heating and humidifications, and in this process what happens, the surface temperature of water surface temperature is greater than T1. T1, and here also for this T1 there are 3 temperatures. T1 is nothing but 3 dry bulb temperatures, T dash 1 that is nothing but 3 wet bulb temperatures, Td is nothing but T dpt temperatures. So, these 3 temperatures will be frequently using. So, what happens in a heating and humidification process, Ts is greater than T1, that can be seen here, but what happens physically, the mean surface temperature of water is greater than the dry bulb temperature of the air. So, water needs to be heated externally. So, now to achieve this process, this water when it is circulated from the pump has to be heated. Only when, that means this external heater or cooler will only act as a heater. That means, if you want to achieve this process, we have to heat this air. If you talk about the process 1 2B, that means we are going in a same line, constant dBT line upwards, and in this process what happens, temperature dry bulb temperature does not change, but humidity increases. So, it is a only process of humidifications, where Ts is equal to the T1, T1 is nothing but dry bulb temperature. In this one, the mean surface temperature of water is equal to dry bulb temperature of air. So, through this process your enthalpy of air increases. Now, if you look at this enthalpy axis here, so this is enthalpy axis in the psychrometric chart, and in this case it is a increase in the enthalpy, if you go along this scale, enthalpy scale, so in this direction if you say it is an increase in the enthalpy. So, what happens in the process 1 to be, the mean surface temperature of water is equal to dry bulk temperature of air, enthalpy of air increases. So, water needs to be heated externally. Now, moving to process 1 to 2C, then that means we are in the process 1 to 2C. So, here we can see the temperature drops, but it is air is getting humidified. So, it is a cooling and humidifications. So, what inferences we can have? We can think this wet bulb temperature T dash is less than T s is less than T 1, that is T dBT. So, the mean surface temperature of water is less than the dry bulb temperature of air. So, here air is cooled, but its enthalpy increases due to humidifications. Of course, here also the enthalpy increases. Enthalpy increases means from with respect to point 1, that is initial state. So, water is heated externally. Now, moving to process 1 to 2D. So, it is a situation that we are going along a adiabatic saturation process. So, this adiabatic saturation process means it is a, we can have, we are going in the enthalpy scale, we are going along a constant enthalpy line. So, we reach this point S, and that when we point reach, we reach this saturation wet bulb temperature for that air at state 1, and this process 1 to 2, but our process terminates at 2D. So, process 1 to 2D, here T 1 dash is equal to T s, and this is the case of pumped water recirculation without any external heating or cooling. So, it is just a the external heater or cooler has no role when you are going in the process 1 to 2D. The recirculated water reaches the equilibrium temperature, which is the thermodynamic wet bulb temperature of air. Then we have other processes, that is process 1 to 2E. So, it is a cooling and humidification. You can see 1 to 2E is a cooling processes, temperature drops, and humidification. Of course, humidity ratio is increases when you go from 1 to 2E. So, here the process is similar to 1C, but with a difference that enthalpy of air decreases and water is required to be cooled externally. Now, moving further, when you are moving along a process 1 to 2F, that means we are moving along constant humidity ratio line or constant omega line. So, in that way we reach T s is equal to T d, that means temperature of water is equal to dew point temperature of air. So, the air is required to be cooled externally. Then we move to process 1 to 2F is cooling, and where till T s is equal to T d. So, the temperature of water is equal to dew point temperature of air and water required to be cooled externally. And the final process is 1 to 2G. So, in 1 to 2G, if you look at this process, so here it is a cooling and dehumidification process. So, T s is less than T d. So, here the mean water surface temperature is lower than the dew point temperatures. So, if you can see, the dew point temperature of air is here, but actual temperature at 2G is less than dPt. So, the air is simultaneously cooled and dehumidified. So, when by this cooling dehumidification process, that means in this process air is simultaneously cooled and dehumidified. That means here there is again there is no role of external heater or cooler air, because your air is simultaneously cooled and dehumidified if you are going along the process 1 to 2G. So, in this way, so these are the possible means of psychromatic processes, or we can say conditioning of air, and that is a requirement for year round air conditioning applications. So, any process you choose on this, that is 1, 2A, 2B, 2C, 2G, 2F, 2G, and if you are able to locate those states and if they are feasible in the psychromatic chart, and such a process exists and we can do for air conditioning requirement. So, that is the novel innovativeness for this particular chart, which says or through the concept of air washer, which says that air washer provides affordable means of year round air conditioning systems. Of course, in towards the higher study in this area, we can have much more feasible processes, that is that, or maybe more advanced topics are available. So, which is not part of this course, but just to say that what are the different air conditioning processes, and that can be which can be achieved through air washer concepts. So, there is some other term people use here in terms of air conditioning systems. One way is that we talk about humidifying efficiency of an air washer, or which is also referred as contact factor of a humidifying coil in air conditioning systems. So, these terms we will be using, and just to give some glimpses, we can define this humidifying efficiency eta H is nothing but, for if you take any state, find the state 2, that is H 2 is nothing but at state 2 and H 1 is nothing but enthalpy at state 1, omega 1, omega 2 is the humidity ratio at state 2, omega 1 is the humidity ratio at state 1. If we can have this, then we can find out the two parameters. One is humidifying efficiency in this fashion, that is actual change in the humidity ratio or actual change in the enthalpy divided by the maximum possible enthalpy change. So, this is first factor. Other factor would be actual change in the humidity ratio to the maximum possible change in the humidity ratio. So, just a other terminology would be a factor what we call as x, which is nothing but bypass factor. So, the same expression is represented in a different way, that is omega s minus omega 2 divided by omega s minus omega 1. So, if you arrange this particular fashion, then we can say the bypass factor and humidifying efficiency, they are related, that is x is equal to 1 minus eta h. Okay. So, with this I conclude this air washer as well as the cooling towers. Now, we will try to solve some numerical problems what we have discussed so far. So, the first problem is based on the cooling tower, for which we have already made the modeling, and this is the schematic diagram of this cooling tower. What it says, but there we have just represented in terms of mathematical modeling. Here we will put some realistic number and try to see that what are the typical requirements or applications, or in way that a power plant expects in a what it says is that this particular problem is mainly dealt with a realistic power plant with some numbers. So, where water enters a cooling tower at 38 degree centigrade with a flow rate of 50 into 10 to the power 6 kg per hour from a condenser of a power plant. So, if you look at this particular figure here, schematic figure, this liquid water comes from a power plant, and this is comes mainly the component of the one of the component of the power plant, it comes from the condenser, and for which we have m dot 1 is 50 into 10 to the power 6 kg per hour, and we also say T 1 is 38 degree centigrade. Stream of cooled water is returned to the condenser at 30 degree centigrade, but with same flow rate. That means, if you say, so this circulated water that again returns to condenser. So, m 2 dot is same as m 1 dot, and your temperature requirement is it has to be 30 degree, and makeup water is added. We do not know how much makeup water needs to be added, to the cooling tower in a separate stream, but what we can say makeup water is added, which we do not know how much quantity, but it is at temperature T5, that is equal to 20 degree centigrade, right. And then comes back to air. So, air comes at state 3. So, atmospheric air enters at 25 degree centigrade. So, we can say 3 is equal to 25 degree centigrade and phi 3 is equal to 35% RH, 35% the relative humidity. Moist air leaves, that means condition 4, T4 is equal to 35 degree centigrade. So, it is at just 10 degree increase in the temperature and it is phi 4 is 90%. So, air gets humidified by 90%. Okay. So, now the what is our requirement? We have to find out m dot A and m dot 5 and of course, approach A and range R. Now, to solve this problem, first thing that we need to do, for condition of air at state 3 and 4, we have to refer this psychrometric chart, and for all liquid conditions we have to refer steam table data. So, let me note down this from the psychrometric chart what information we can get. So, we can say at state 3, that means at these conditions from referring to, that is 25 degree centigrade and 30% RH. So, if you say 25 degree centigrade and 30% RH, and other state would be 35 degree centigrades and 90% somewhere here. So, from this we can find out data like omega 3 is equal to 0.007 kg by kg dry air, and we also know have to find out that WBT at that location is 16 degree centigrade. We can go along this line and drop a vertical. So, constant well temperature and drop a vertical, then we will have TWBT. And for state 4, we have omega 4 is equal to 0.03, close to this number, because we do not have any data above that. So, 0.03 kg per kg dry air, and from steam table we have to record all this data. So, what data we require? So, we require data state 1, water 38 degree centigrades. So, you can have HF1 159.2 kilojoule per kg Kelvin. State 2, that is water at 30 degree centigrades. So, it will have HF2 is equal to 125.79 kilojoule per kg. State 5, state 5 is water at 20 degree centigrade. So, we can have HF5 is equal to 83.96 kilojoule per kg. This is about liquid state. Now, vapor state, for the vapor state we require at state 3 and 4. So, state 3. So, state 3 water may be in vapor state. So, at 25 degree centigrade we can say Hg3 is equal to 2547.2 kilojoule per kg Kelvin, and state 4 state 4 is 35 degree centigrade. That is for moist air. T1 is 38 degree centigrade, T2 is 30 degree centigrade, and T5 is 20 degree centigrade. So, all these numbers are here. G4 2565.3 kilojoule per kg, and then we have these two important equations which we need to find out. What is the mass of flow rate of air, which is this expression, what is the mass flow rate of makeup water, which is this. These derivations we have already made it. Now, here you have to just use the end results and put these values already noted down from the steam table and psychrometric chart and find these values. So, when you put it, we can find out that m dot A is equal to 50 into 10 to the power 6 multiplied by 159.21 minus 125.79 divided by 3 parts 1.005 into 35 minus 25 first part plus omega 4 Hg4, that is 0.03 into 2565.3 minus 0.007 into 2547.2 minus omega 4 minus omega 3, that is 0.03 minus 0.007 into 83.96. So, the denominator part is this, numerator part is this. So, from this we can find out m dot A is equal to 2.4 into 10 to the power 6 kg per hour, and then m dot 5 is equal to m dot A, that is already 2.4 into 10 to the power 6 omega 4 minus omega 3 is 0.03 minus 0.007. So, m dot 5 is equal to 5.5 into 10 to the power 5 kg per hour. So, you can say this amount of air requirement is there and this amount of makeup water we need to have. Then we have approach and range. So, as I can say, approach A is equal to T1 minus T WBT at 3. So, this numbers is already there. T WBT of 3 is, that is 38, WBT of 3 is, T1 is 38 and T WBT of air is 16 degree, that we got it. So, this number is 22 degree, and range R is equal to T1 minus T2. So, T1 38 minus 30, that is equal to 8 degree centigrade. So, range is 8 degree centigrade, approach is 22 degree centigrade. So, we got all the answers: mass flow rate of air, mass flow rate of makeup water, approach and range. And there is another problem, probably this problem which I would have solved in the last lecture. So, this was a problem in which there is a adiabatic stream, mixing of two adiabatic streams. So, for this mixing of adiabatic stream, I mean there are two streams which comes and it goes as a single stream, and this mixing process we say it is a adiabatic stream. So, you have state 3, state 1, state 2 two streams at state 1 and 2 mix, then goes at state 3. So, this mixing is called as adiabatic mixing. So, the formulation of this problem which we have already done in our last lectures, but due to the limitation of time I could not solve a problem. So, here we will just try to see if this problem can be solved. So, here the problem is there are two streams, one is coming at 2.4 meter cube per second, other is coming at 7 meter cube per second. So, it is a volume flow rate. So, we can say B 1 is 2.4 meter cube per second and B 2 is 7 meter cube per second, and the stream 1 has temperature 5 degree, humidity ratio 0.002. So, we say it is T 1 5 degree, omega 1 is equal to 0.002 kg per kg dry air, and stream 2 has 24 degree centigrade, that is T 2 has 24 degree centigrade, but here we have phi 2 is 50%. So, these data are given, and what we require, what is omega 3 and what is T 3, that is the requirement. So, from this string we can first find out at 0.002 and omega 5 degree centigrade. So, we can locate this particular state here 0.002 and 5 degree centigrade. Another point is 24 degree centigrade 50% RH. So, 24 degree centigrade and 50% RH. So, you can denote this value. So, from this we can get specific volume. One has somewhere around BA1 0.79 meter cube per kg dry air, and we also can find out enthalpy. So, this is about 10 kilojoule per kg dry air. So, similarly for state 2 we can find out BA2 is equal to 0.85 meter cube per kg dry air, and H2 has close to 48 kilojoule per kg dry air. So, somewhere about around this. So, it is H1 and this is H2. Okay. Of course, we require omega 2 as well. Omega 2 will be 0.0094 kg by kg dry air. So, you know all the parameters. So, you have to use two fundamental equations. One is omega 3 is equal to omega 1 into m dot A 1 plus omega 2 into m dot A 2 divided by m dot A 1 plus m dot A 2. And what is this m dot A 1? M dot A 1 is equal to nothing but B 1 by B 1, volume flow rate by divided by specific volume. So, 2.4 specific volume is 0.079. So, this is 3.03 kg per second. Similarly, m dot A 2 is V 2 by small v A 2. So, V 2 is 7, small v A 2 we have already calculated 0.85. So, this number is approximately 8.23 kg per second. So, we have this. So, from this all the data we have, so we can calculate omega 3 as 0.002 into 3.03 plus 0.0094 into 8.23 divided by 3.03 plus 8.23. So, this number will give you 0.0074 kg by kg dry air. So, similarly, we can find out H3 is equal to m dot A1 H1 plus m dot A2 H2 divided by m dot A1 plus m dot A2. So, this number is 3.03 into H1 is 10 plus 8.23 into H2 is 48 divided by 3.03 plus 8.23. So, this means H3 is equal to 37.7 kilojoule per kg. Okay. So, first answer we got omega 3 is equal to 0.0074 kg by kg dry air. Second answer we have to find out for omega 3 and H3. So, if you put 0.0074 on this axis, so somewhere 007 you can have this axis. On this axis, wherever it intersects this H3 as 37.7 intersects somewhere here. Close to this axis, so we can intersect somewhere here. You drop a vertical, we say it is a 20 degree centigrade. So, we can say T3 with respect to omega 0.0074 and H3 37.73, T3 can be approximately 20 degree centigrades. So, we can say T3 is equal to 20 degree centigrades. So, this psychrometric chart helps to locate the moist air states, and we can calculate all the properties of moist air stream using this psychrometric chart. So, with this I conclude this particular lecture today, that is cooling water and air washer, and side by side we also completed module number 5, that is refrigeration and air conditioning. Thank you for your attention.